But they'll join when they can. Thanks again for coming, everybody. Great turnout on this beautiful sunny day. Hope you're enjoying your snack and lunch. Today we have Bob Bostwick come present to us. He's the director of the high-throughput screening facility at Southern Research. Has a lot of experience in high-throughput screening. Used to work in industry as well, so he's got a plethora of experiences to build upon and expand upon. So I think it will be a really nice illustration of how you can use robots to do drug discovery and really sort through lots of potential compounds that may ultimately one day be a starting point for a drug discovery program. We're going to let them take it away. And also at the end, last week, some of you already signed up for a high-throughput screening tour. So you'll see probably some videos of the facility in the presentation today. But on March 11th, at spring break, there's an optional tour of the high-throughput screening facility at that time. We'll meet at Southern Research. It will take 20, 30 minutes or so. So we'll just be over lunch as well. I'll keep this, sign-up sheet here in the front. So if after today's presentation, you're so inspired that you didn't want to see robots yet, but now you totally want to see robots, you still can. It's robots. Cool. All right. Bob, take it away.
Okay. Thanks, Micah. So, as Micah said, I'm going to talk to you about high-throughput screening, which is a process that we engage in usually in very early or initial phases of the drug discovery program. So I'm just going to put that into context for you, and then tell you a little bit about not only what high-throughput screening is, but how we do it, how we execute it. With that, let me just start off with the overall process of drug discovery, which maybe you've seen this before, but basically we typically divide it up into three broad areas. The phase we call lead generation. Then there's a phase called lead optimization, and then candidate selection. And the terms lead and candidate refer to compounds. Okay, so when we're talking here, we're talking about generating compounds that can be progressed through this pipeline of activities all the way to the final candidate, which could hopefully become a drug. Okay, but before we engage in any kind of chemistry, it's important to know what we're looking for. So the very initial event in the drug discovery process is to identify the target that we want the compound to engage with. That's the molecular target, like a protein, for instance, an enzyme, for instance, that its function can be regulated in a disease process. So we think, for instance, like in cancer, if a certain protein is upregulated, then if you can inhibit the function of that, then you might be able to ameliorate the effects of that and correct the pathological defects. So that's the very initial phase in the process. And then, of course, the validation of that target vis-a-vis its pathological effects are important. But once that's done, then we want to engage in this process of finding compounds which engage the target, or which can affect the activity of the target, or affect the biological outcome of that aberrant activity of that target. So in order to find compounds, one of the ways we do that is to utilize high-throughput screening. Because high-throughput screening basically is an unbiased random approach to finding compounds for targets that we don't really know what types of compounds can interact with them. And so I'll describe that process. And then along with that goes the medicinal chemistry efforts, because it doesn't do any good to identify the compounds if you can't do something with that information. So it goes hand in hand with the medicinal chemistry effort to take the information that comes out of high-throughput screening and then engage in a drug discovery activity. So the other downstream events of this you'll learn more about in the course of this program. But so let me just focus in on this initial event here. And first of all, to say that high-throughput screening is really only one way of determining initial starting points in the drug discovery process. There's other ways to approach this, which are not mutually exclusive. They can be combined with high-throughput screening, or can be engaged in independently. Virtual screening, for instance, if you know what the molecular target looks like, you have a crystal structure of it, for instance, then you can, through the in silico process, find compounds that can dock to the binding sites of that model. So, for instance, that can be utilized as a way to find starting points. Or if you know compounds in the literature already that have been reported to be, say, inhibitors of a certain enzyme. You can rationally design other compounds around that structure, use that structural information for that. So HTS is just one way, but it's an important way and a very popular way for initiating drug discovery. So just to get some of the vernacular clarified for you, I'll talk about a hit. When I'm talking about a hit, I'm talking about a compound that gives a validated response in the screen. Okay, so it's not just one that comes out of the primary screen, but one that we validated to say that it actually is engaging the target. For instance, we know it's inhibiting the enzyme and not affecting the readout of the assay through some off-target mechanism. Then a lead is a compound that's been confirmed by one or more orthogonal assays, in addition to the one that we used to find it. And usually we like to have in vivo data to classify a compound as a lead. That's because we don't want to put a lot of chemistry effort into compounds that aren't going to work in vivo. And then finally, the drug candidate, which is the compound that's optimized for its activities, not only at the target, but also built-in drug-like properties, so the ADDA properties that are also important for a compound to be a drug. So, okay, zooming in a little bit more on this initial process where HTS fits in. So again, after identifying targets, then it's important to develop an assay if we're going to run it in hypertrophic screening. So that assay has to be amenable to hypertrophic screening. So the strategy that we employ for that assay and the feasibility of that assay to run it in hypertrophic screening is important. We have to assess that early on before we put a lot of effort into it, because obviously we don't want to get up to the point of running a screening and it doesn't work. So there are certain technologies that have been invented specifically for hypertrophic screening, and I'll mention a few of those later on. But once we've decided what the assay is going to be, then we need to develop it, and we need to optimize it and validate it to know that it will run in hypertrophic screening in a robust manner. And once we've done all that, which actually is most of the work in terms of getting an assay to work in HTS, we spend a lot of time doing that up front. Once we've done that, then it's a matter of just kind of turning the crank when we run the primary screen. So that's when we actually screen all the compounds through that assay, and then we confirm them as being active. We read in a retest of that assay. And then finally, we identify compounds which are members of a series of compounds. Okay, so we're not looking for just one compound, we're looking for classes of compounds that we can group into series. And so we engage in this activity called active to hit, where there's a little bit of chemistry effort here to see if these series can be expanded through some initial medicinal chemistry efforts to know that, in fact, we do have a hit series that's amenable to progression. So really, what we're looking for in hypertrophic screening is not to find, a drug. We're really looking for chemical assets that can be identified as starting points for regeneration. Okay. So what is HTS? Well, we define it as a process really through which a large number of compounds can be interrogated. And these are always in vitro assays. And they're run in very small volumes, usually in robotic platforms. And they detect either a phenotypic or a response that lets us know that we're engaging in target of interest. Okay? So sometimes for phenotypic assays, we're not always sure of what the target is, but we should have a way of identifying that in subsequent assays. Why are we doing that? Because, again, as I mentioned, we don't know what kind of compounds are going to engage the target, are going to have the biological effect that we're looking for necessarily. So it's a way to randomly just screen through a collection of compounds which have drug-like properties and to filter out really those that don't do anything, okay? So that we're left with a manageable number of compounds that we can interrogate through other assays, maybe in a slower throughput fashion, to really hone in on the ones that are going to be the most promising. So the way we perform hypertrophic screening is, as I mentioned, utilizing robotic platforms, but it's more than that. You have to have people that are specialized in developing and running the assays and operating the equipment. They have to be familiar with the specialized assay technologies that have been developed for hypertrophic screening. And then we also have to have a process of managing the large collection of compounds and getting those compounds into our assays. and then we have to be able to analyze this large amount of data that comes out of it. So really there's three major components in a high-temperature screening campaign, and all of those components really require specialized capabilities. So the whole process is done by a team of people, not just one person. So this is a list of the targets, the projects that we've screened so far in high-temperature screening for the ADDA program. Almost equally divided between cell-based and biochemical assays, and these are some of the assay methods that we've used to run those assays, and almost all of them exploit some measurement of light, fluorescence or luminescence, usually. And then we're screening about 200,000 compounds in a campaign in this program. Okay. So this year we've done 22 campaigns so far. This year we're doing one more. We're revisiting CD38, but we're using a cell-based assay, so the biochemical assay, to see if we can't pull out some different types of chemical assays. Okay, so what are the components then of high-temperature screening? So I briefly mentioned that. First, we need a compound collection. Can't do anything without the compounds, and the properties of the compound collection turn out are very important. When HTS first started, all the chemical companies just screened everything they had, including paints and dyes and all kinds of stuff that would never, ever be drugs. So finally, after kind of going down that black hole, we realized that we really needed to define the collection that we screened. So the first thing to do is to make sure they have drug-like properties. There's certain parameters that can be utilized. We typically use about 8 different molecular property parameters, like molecular weight, polar surface area, number of hydrogen bond donors, acceptors, and so forth, to define the properties of the collection. That's based on known drugs, what people already know about compounds that are actual drugs. So we put together a collection which has these kind of properties out of the universe of compounds that are out there. Then we also want some of the compounds to share structural features. So usually you want clusters of compounds with similar structural moieties within your collection. And that's because you really need multiple representatives of compounds within the same cluster when you run an assay, because the idea, again, is not to find one compound, it's to find that structural motif that the chemist can build off of. So every compound within a cluster may not come up active in the screen, but if you can identify, 1 or 2 or 5 of them, then that gives you confidence that, this could be a real effect in the assay. So typically, in a collection of 1 million compounds, you'd want to have about 50,000 clusters in there, which means that you'd have about 20 compounds that represent each cluster. That way you can be assured that you will identify the clusters that represent the structures that are active in the assay. So, okay, then the other component is the assay. What do we need for that? Well, first of all, as high throughput says, we need throughput. We need to be able to run the assay in a time frame that is conducive to working your way through several 100,000 compounds. So typically, most of our assays we run in batches that enable us to screen about 32,000 compounds in a day. Sometimes this can be higher. We've gone up to 100,000 or more in a day. Sometimes it's a little bit less, depending on the assay, but typically we're running around 32,000 a day. Then it has to be friendly to the automation platforms. So that means that the assay really needs to be homogeneous. That is, we need to be able to just mix the components together and read. We don't want to do separation steps. We don't want to do wash steps, things that require a lot of manipulation. Just adding the components together and then reading the sieve, because robots do that really good. Usually, we also run them in microtiter plates, and I'll show you what those look like in a minute. Either 384 or 1536 wells per plate. Each well has one reaction in it, so each well has one individual compound in it. So a 384 well plate, accounting for the controls that we put on the plate, we can test 320 compounds per plate. Likewise, in a 1536 microplate, we run about, I think it's 1280 compounds in one of those plates. So that's because these plates have to be compatible with our liquid handling systems that we use. And they also have to be compatible with the library format that we have. Then again, because we're running so many tests, that has to be cost effective too. If it costs $1 a well to run the test, and if you screen 1 million compounds, that's $1 million. So most people aren't going to spend, even pharma companies aren't going to spend $1 million running a high-throughput screen. So we need to get this down to pennies per well in terms of the cost. But if we go to 1536 in particular, usually the reagent costs are contained by that because we use very low volumes in those assays. And then finally, the assay has to be robust. That is, we have to have a large signal window, and the variability around those windows has to be relatively small. And I'll go into that a little bit more. So then the third component is the informatics. That is analyzing the data, collecting the data, managing the data. And so we have a lot of different systems that enable us to do that. All the data is collected in an Oracle database. So the data comes off the readers into that database, and then they're processed in a software program we call QBase, which basically analyzes the data and can generate, concentration response curves as if we need them. And then that data is also, it's at that point that the compound data is matched up with the identification of the compound. Okay, so all the compound samples have an ID number associated with them. So we have to know that this compound is in this well, and this is the data that goes with that compound. So this software makes that association. Then, of course, all the data is stored electronically in a notebook, and that can be accessed by the chemist through another software system we have, Informatics, where they can see the biological data as well as the chemical structures. And they can collect all the biological data for that chemical structure through that software program, not just for the screen HTS assay, but all the assays that are run for that compound. Then we have a system called Pipeline Pilot that the chemists and our informatics people use to basically analyze the compound collection, for instance, and look for associations between compounds. And then finally, in parallel, we have a system called a Laboratory Information Management System, or LIMS, which allows us to track everything in the process, including all the usage of instruments and reagents and so forth. So that's very important to be able to track all that. So each one of those processes requires, like I say, certain specialized capabilities. So we have people that just do the compound management part. We have people that just do the assay and screening part. We have people that just do the informatics part. So that really enables us to work more efficiently. Okay, so moving on to the steps now in HTS. So as I mentioned, the first thing is to select an assay and then develop and optimize it. And after we optimize it, we have to validate it in the HTS mode. So that means we have to run it on the robots to make sure the assay is going to perform the way we want it to when it's automated. Okay, not just when we're doing it by hand. And usually the final step of that process is to screen a collection of compounds. Usually we take a subset of about 10,000 compounds. We run them in the assay to see what the data looks like, and then we run it again, and then see if we get the same data. So if it's reproducible, do the same compound samples give us the same readout in the assay when we do it twice. So that tells us about the variability of the assay, and also tells us a little bit about what kind of hit rate we can expect from the screen. So it's a very important step in the validation. But once we've done that, then we can run the screen. And as I mentioned, primary screening usually between 200 and 800,000 samples. We typically do about 200,000 in the ADDA program. And so the component of that is we're running that to find the hits. So hit selection and then hit confirmation. Not only confirmation in the primary screen, but also we run almost every screen, we have to run at least one counter screen assay on the hits. And that is because you'll always find compounds that can affect your readout. So for instance, if your readout is fluorescence and you're looking for a decrease in that signal, the compound that can interfere with fluorescence, can quench it, for instance, could come up as a hit, but it's not affecting your target, it's just affecting the readout of the assay. So you set up a counter screen assay to tell you that, to tell you that if your effect is real or if it's off target. And that way we can eliminate all the compounds that aren't real. And then there's a chemistry triage of those hits, so that the chemist then will look at the structures and they'll determine which ones are more amenable to medicinal chemistry going forward, so we can further narrow down the chemical space that we're going to look for subsequent to the screen. And then, of course, all those compounds are subjected to secondary assays, again, to validate, to make sure that they give us the biological response that we want. And then after that, we go into a full-blown medicinal chemistry. So let me just talk a little bit about assays and assay strategies. So basically, when we are selecting assays, we have a first choice is whether we want to run a phenotypic assay or we want to run a target-based assay. And by that I mean a phenotypic assay is an assay in which we are looking for a certain biological response. Say we're screening for an anti-cancer drug, and we have a certain cancer cell, maybe with a specific mutation in it, but ultimately we want the compound to kill that cancer cell, okay? So we can just look at cell viability. That can be a measure, and that's one we use all the time to screen compounds, because obviously we want to find compounds that are going to kill that cancer cell. However, that doesn't tell us how the compound is working. We don't know, if it's hitting the molecular target that we're interested in. We just know that it has a biological response. That's okay. We can do that so long as we can determine downstream events how it's working. So these are phenotypic assays are typically cell-based assays. Again, the drug target is usually unknown, and so then we use physiological or phenotypic readouts like, say, reporter assays or cell viability assays. Receptor assays, ion channel assays are also fall in this category. Target-based assays can be run either as biochemical or cell-based assays. And in that case, the drug target is known, and the readout measures the direct interaction of the drug with the target. Okay, so we get information about drug-target interaction. So these kind of assays are like binding assays or enzyme assays or receptor assays in cell-based format. So these two approaches are not mutually exclusive. In fact, usually when we run a screen, and say if we do a phenotypic screen, then we need some kind of secondary assay that tells us about the target, so we can measure target engagement, and vice versa. If we run a target-based assay, then we want some phenotypic assay that tells us we're getting a biological response. So really, they kind of go hand in hand. But oftentimes we can choose between the two approaches for which one we want to use for high-throughput screening, and usually that's determined by which assay is more amenable to the screen. So just a little bit about biochemical versus cell-based assays. So biochemical assays have certain advantages over cell-based assays in that they're simple, usually. They're more consistent in terms of their ability to control all the parameters a little bit better. Again, they can give a direct measurement of target engagement of the compound. We also can look for specificity of compounds in these kind of assays. So if you want a compound that only inhibits a certain type of kinase, you can measure that and compare it to assays for the other kinases. And of course, we can also measure certain characteristics like kinetic constants, for instance. That will be important. But the disadvantages of that are that it's usually a non-physiological condition. So you can set up an assay, but it doesn't really tell you, how that compound is going to work in a biological, in a cell-based or more biologically relevant context. And it's not sensitive to other properties of the compounds that are ultimately going to be important. For instance, their ability to penetrate into a cell, the types of toxicity the compound can have on cells, and the off-target effects it can have. So again, useful for screening, but you're still going to need other assays to mitigate these responses. Likewise, for cell-based assays, it's almost the opposite. The advantages there are, mitigate the disadvantages of the biochemical assays in that they are more physiological assays, and they're amenable to looking at, how systems work in cells, and they also are sensitive to some of the other properties of compounds that you don't pick up in biochemical assays. But then vice versa, they're not a direct measure of target engagement usually. They're more complex, more highly variable, and they will exclude compounds that typically are less soluble that might still engage the target. You just, they don't have the right chemical properties. Okay, so in terms of the different kinds of cell-based assays that we can use, we usually, one of the formats that we like is to look at fluorescence intensity of some signal in the cell. This is an example of measuring fluorescence intensity in cells that can be generated through the induction of a reporter protein, say a fluorescent reporter protein like GFP, or detection of proteins that you can measure with a fluorescently tagged antibody, or even the production of molecules that you can bind to beads that can fluoresce, so you can determine the effect of a compound that way. So for this type of assay, we use a format we call laser scanning cytometry, which basically can detect. This is what a picture of a well looks like. And you'll notice that it discriminates these little dots, which can be either cells or beads. They can discriminate objects. Okay, so it turns out that in this well, there's a lot of fluorescent protein or signal sometimes in the solution, but we don't pick it up in this assay because it only measures what the fluorescence is associated with the objects, because that's why we like to use this. So it's similar to like running an ELISA assay or even a flow cytometry assay, except you don't have to have any of the separation steps. So it makes it very amenable to high throughput screening, because as I mentioned, we don't like to separate things. We don't want to wash things. So we use this technology a lot. The particular instrument we use is called the mirror ball. But basically, you can use this for these types of cell-based measures. Another type of fluorescence intensity assay we use is a biochemical assay. It's called fluorescence polarization. And that is based on the principle that a fluorescently tagged molecule will rotate rapidly in solution. And when you excite that fluorophore with fluorescent light and then measure the emitted fluorescence through polarized filters, you can have a filter that's perpendicular or parallel to the excitation light. Then you can measure those two different fluorescent signals. Now, if a compound is rapidly tumbling in solution, it won't matter if you measure it in a parallel or perpendicular manner through the filter. You'll get about the same level of fluorescence. But if it's bound to a larger molecule, then it won't tumble as rapidly. And so now you'll see a difference in the emitted fluorescence through those polarized filters. So we call this a fluorescence polarization signal. And it's calculated by this formula, which will increase, when you're in this state. So if we're just measuring this binding event, we can look for an increase in the FP signal. If we're looking for a compound that can inhibit the binding of this small molecule with this larger molecule, then you look for a decrease in the MP signal. So the types of assays we can use for this are receptor and ligand interactions, or protein peptide interactions, DNA protein interactions. It's also been used a lot for tyrosine kinase assays, because you can measure you can tag your fluorescent, your phosphorylated peptide with an antibody, which is a much larger molecule. Another type of fluorescence assay that we use in biochemical format is called a proximity-based assay, and that's where you bring two molecules together to generate your signal. And there's basically two flavors of this. One is called FRET, or time-resolved FRET in this example. Another is called alpha screen technology. The technologies are different, but the principles are kind of the same. And that is that if you have an analyte, say something that you want to measure, and you have two antibodies that can bind that, like you would in an ELISA assay, you can bring in a lanthanide, which is caged in a way that it excites, it emits fluorescence when it's excited. So in this case, it's a europium chelate. And on the other side, on the other antibody, you can conjugate it with a molecule that will accept, or itself is fluorescent when it's excited in the right way. And the way this works is that when you excite the chelated lanthanide with light, usually at 320 or 340 nanometers, then that will emit fluorescence at 615. However, if it's in proximity to this molecule, then there'll be what's called a Fourier resonance energy transfer from this. When you excite this molecule, then some of that energy will be transferred over to this molecule. And now that's enough to excite this molecule to fluoresce. But it fluoresces at 665, not 615. So in the assay, you can measure the change in fluorescence of the 615 signal relative to the 665 signal relative to the 616 signal doesn't change. And you can measure whether you got this association or whether you inhibit that association. So you can go both ways with it. Likewise, with alpha screen technology, which is short for Amplified Luminescence Proximity Homogeneous Assay, you have a similar phenomenon in that you have to bring two beads, in this case, close together. One is called a donor bead, one's called an acceptor bead. The chemistry of the donor bead is such that when you excite it, in this case it's 680 nanometers, it produces a singlet oxygen, okay? And so it's this oxygen which then interacts with the chemistry in the acceptor bead to first cause a molecule inside that to luminesce, and then that luminescence of that molecule will excite a fluorescence of another molecule inside the acceptor bead. So you measure fluorescent signal. So that's why it's called amplified luminescence, because you're really measuring a fluorescent signal, but it relies on the luminescence signal that's set up by the singlet oxygen reacting with the chemistry here. But it's still the same principle. You have to bring these two beads in proximity with each other, so some kind of interaction. In this case, it's a protein interaction as the example. So again, these types of assays can be utilized to detect, say, the product of an enzyme action, or you can measure ligand displacement in competition assays. You can measure association of proteins, two protein partners binding, or you can measure dissociation. So for instance, cleavage of a peptide and a protease activity that has both of the acceptor and donor molecules attached to either end of it. So then another example of luminescence is a reporter cell-based assay. We use this quite a bit. In this case, what we're doing is you have a promoter that you've identified, say, to some molecular target that you want to affect the level of that protein in your cell, but you can engineer it so that that promoter sequence is upstream of the gene for luciferase, which is an enzyme that will, once it's produced in the cell, you can add a substrate to it and you get a luminescent signal. Okay, so simply by activating this promoter, you get more luciferase message transcribed, and when it's translated into the enzyme, adding a substrate, you get light. Now, there's basically three types of luciferase molecules out there that can be used for this. One is has been identified for firefly luciferase. Another one is Ranella, and then finally there's an engineered type called Nanolux, and this is totally engineered, but it has a lot of advantages over the firefly and Ranella. As I mentioned, you have to add a substrate to the enzyme to get the luminescent signal. Luciferase relies on the presence of ATP in order to work, okay? Whereas Ranella and Nanolux, you don't need ATP. You can just have, add the substrate for those respective enzymes. They get a product plus luminescence. So the advantage is that, luciferase, the peak emission is separate from where either Nanolux or Ranella would be used. So a lot of times you can use these together in the same assay and measure both signals simultaneously. But the real advantage of the Nanolux is, in addition to its low molecular weight, is that it has much brighter characteristics. So in fact, you get about 1,000-fold more signal per molecule of Nanolux than you would for luciferase or Ranella. So we tend to use the Nanolux in our reporter assays when we want to do this, because we just have a much stronger luminescent signal in the assay. Now, for cell viability assays, again, you can have different formats that you can measure. You're all probably familiar with MTT, in which you measure absorbance as a readout from the transformation of this substrate to its product through mitochondrial reductase activity. Alamar blue gives you a fluorescent signal through similar types of metabolism. And then finally, there's cell target glow, which measures a luminescent signal, and this again exploits luciferase, which you add in this case to the cell. But what you're really measuring in this case is the content of ATP of the cells. So either mitochondrial enzyme activity or ATP levels, or different ways you can measure cell number and cell viability. So we use this in proliferation cytotoxicity assays, and here's an example we call this a cytopathic effect assay that we use in a lot of our virus screens, where you add a virus, you have cells that are not infected with the virus. When you add the virus kills the cell, and you can see the decrease in the signal. When you add a compound that is antiviral, that inhibits the virus, and you get the signal back. Okay, the cells survive. Then finally, we've utilized qPCR in high-throughput screening. We don't do this a lot, but we do have a method that enables us to use that. And the advantage here is that we can look directly at gene expression levels in cells. This is useful particularly for bacteria and virus screens, where we want to look at the mRNA content in the cell. Okay, now let me talk a little bit about the assay development part of it. So you may be familiar with running assays in tubes with handheld pipettes, but what our assays are really executed on a robotic platform. So when you go from here to here, there's certain characteristics you have to pay attention to. So first thing is that all the assays are run in microtiter plates, because the robots basically grab the plate and move it from station to station. So everything has to be in a common format. So these are examples of microtiter plates. You can have 96 wells per plate, 384, 1536, or even 3456. And you can see that the dimensions of the plates are the same, the outer dimensions. It's just the number of wells inside the plate that's different. And each one of these wells has different volumes, of course, which dictates what type of assay you can run in them. Typically, in order to get throughput of 30,000 to 100,000 data points a day, we have to run either in 384 or a 1536 well plate, which means in 384 well plate, we're running assays in 25 to 50 microliter range, and in a 1536 well plate, each assay has 4 to 10 microliters. And I've got some examples of these plates here. They come in different plastics. It depends on what your assay is, what type of plate you want to use. This is just the density of the vessels. So when you're optimizing an assay, then you have to pay attention to this parameter. What type of plate, what density you want to use. Also, all of our compounds are solubilized in stock solutions of 100% DMSO. Okay, that's just the way that industry has kind of adopted that, because DMSO is more or less universal solvent, and compounds are relatively stable in DMSO if you store them properly. But that means that every assay that we have has terminal DMSO in it. So we have to measure the tolerance of the assay for the content of DMSO. So that's one of the first things we typically do in assay optimization. Then we have to characterize our reagents in terms of stability. So for instance, if we're using an enzyme, we have to know how stable is that enzyme, not only in terms of storage, but also in terms of the time frame of the assay itself. So if we're running an assay that's going to take, say, 5 hours from the first plate to the last plate, we need to know that that enzyme is going to be stable over that 5-hour interval at room temperature, or on ice, where we maintain it during the course of that assay run. So we have to work out the pre-incubation requirements for that, and we want to stir, cool, heat reagents, how stable they are for there, and then also the quantity that we'll need in the assay. So then we also have to identify how do we add the reagents. As I mentioned, we want add and read type assays without any washing, but the order of addition can be important. So if you have an enzyme assay, you have a substrate, you have maybe a cofactor, you have buffer, the order in which you add these things can sometimes affect how the assay runs. So we have to work all that out. The number of additions is also important. The fewer the better. We try to run assays that really don't have more than 3 additions. Sometimes you can go up to 5 or 6. But anything beyond that gets kind of complicated. And again, the volume, we have to pay attention to the volume that we run in the assay. If we're running a cell-based assay, of course, we have to have enough cells to support that assay. So we have to know what the growth characteristics of those cells are, how we can scale them up to get the number of cells that we're going to need in the assay, and whether we have to maintain those cells continuously in culture, or whether we can freeze them back and pull out batches of cells from frozen stocks as we need them. Okay, assay performance. So this is very important in high-throughput screening because when you run high-throughput screening, what you're doing is you're only testing one compound at one concentration one time. So you want to know that your assay is robust enough to be able to detect whether that compound is active or not. So we utilize statistical measures to do that. The first thing we need to do is to measure the strength of the assay signal in the assay. And typically, so we use the signal to background or signal to noise ratios to determine that. Usually for an assay that can run in HTS, we need at least a 5-fold signal to background window. This is usually around 15-fold here for signal to noise. So that's the first indication we have of whether an assay is going to work or not. The other thing is we have to have low variability, so we measure that with coefficient of variance. When we calculate the percent CV, usually the percent CV needs to be 10 or less if we have a signal to background ratio of 5. Then the assay has to be reproducible, and that means that well to well we need good reproducibility. Within a plate, we also need reproducibility plate to plate within the assay, and also day to day, because it takes several days and usually weeks to execute an HTS campaign. So we want to know that we can get consistent data throughout the entire process at every level in the screen. Okay, so then how do we know if the assay is actually ready to run an HTS? Well, here we rely on a statistic called the Z-factor. And basically, this is calculated from the measures that I just mentioned, basically sample means and the standard deviations around those means. If you look at the way data is populated, particularly large data sets, if you have a well-defined assay, you'll usually get a Gaussian distribution of the data. That is, say for control data where you don't have any effect in the assay of compounds, they will distribute around a mean value, and 3 standard deviations to either side of that mean will contain 99.7% of all these compounds in that population. So that defines the distribution of the data for that population of compounds, which are basically compounds that don't have any effect on the assay. Likewise, compounds that do have an effect on the assay will similarly distribute around its own mean, and you'll have similar statistics in terms of standard deviations. Now, the Z-factor can be calculated from those parameters, so that if these populations are well separated, you can measure the strength or the distance of the separation band with the Z-factor. So that if they're well separated, the Z-factor will calculate through this formula to give you a value of between 1 and 0.5. Okay, so if anything above 0.5 in the Z-factor tells us that this is a robust assay, we get a good separation between no effect and effect in the assay, and we can determine if a compound is part of this population or part of that population. If they're less than 0.5 and greater than 0, then that means that the separation band is small, and we can't always our confidence of determining whether a compound belongs here or there to which population is not as strong. So we tend to not want assays that run less than that. And of course, if it's 0, these bands touch, and if it's less than 0, they overlap, so it's useless. So again, we're looking for Z-factors with values of 0.5 or better. So in a pilot screen, then, this is the assay validation final step. As I mentioned, we run a small collection of compounds twice. We do it on different days, same collection of compounds, and then we compare the data that we get off both of those runs. So if we just tested a few compounds, we don't really get a representation of the diversity of the collection. So we really need to, this is more in a high throughput context. So 10,000 is about the right number to run in a validation set. So we can do a statistical analysis of that data, just like we would do for a screen. So it enables us to determine the reproducibility of the assay, the approximate hit rate that we have, and whether we need to adjust anything in the assay to bring the hit rate up or down. So, for instance, that can be done by adjusting the concentration at which we screen the compounds. We usually screen at 10 micromolar, but if it's a high hit rate, we can reduce that down to 5 or 3 micromolar. If it's not high enough, we can increase it a little bit higher. And then it'll also tell us if we need to run a counter screen in parallel. If we're just getting too many compounds that have off-target effects, then we'll know, well, we also have to run another assay alongside of it to determine what the real hits are. So this is an example of what two separate runs of a validation screen would look like. So each dot represents the data values for the same compound run on day 1 or day 2. And so if it's a good reproducible assay, then the data should line up pretty well and we get good correlation between those data sets. But if we don't get good correlation, then it tells us that something's wrong with the assay. Even though the Z factor in this particular data set was good for both assays, what it tells us that really here we're just picking up off-target activity. We're not really finding much in terms of on-target activity in the assay. So we have to go back and rework that part of the assay to make sure that we're getting our data to line up this way. Now in the primary screen, once we've done the validation, we go into the screening. Each compound, I said, is tested once at a single concentration. And this is to maximize the number of compounds in the series that can be tested. Instead of testing a smaller number of compounds in multiple replicates, it's better to test compounds which are in the same series, but just test them once. So that because we're trying to pull out that series of compounds, not just that one compound. So this will mitigate the risk of false positives, but we want to make sure that those compounds are typically not on the same plate, because we could get plate effects that could mislead us. So the plate layout in a 3-to-4 format is usually like this. We have the outer two columns that contain our negative controls. And these outer two on this side contain our positive controls, and we usually have a reference compound down here in this corner. So when we run the assay, what we can do is we analyze the data, and this is a heat map of what that data will look like. So the negative controls will have no signal, the positive controls will have our full signal, and then the hits will be something in between that. The test compounds either won't have any signal at all or be very faint in the assay, but the hit compounds will have strong signals, similar to the positive controls. And depending on what our cutoff is, we can define, say, these 3 compounds, or maybe these 4 compounds as hits, and the rest of them won't be. So we can determine from this where we want to do further investigation to find which compounds are in fact working. So this, of course, assumes a random distribution of compounds in the library, because if they all lined up in this row here, then we would think there might be something wrong with one of the pipetting issues or things like that. So if you see plate patterns, it indicates there's something going wrong with the process and they're not real hits. So we determine that by looking at ratios of, left to right, top to bottom, inner wells versus outer wells, and so forth. Those ratios should match up and be about 1. This is the example control data from a real high-throughput screening campaign that we ran. And you can see that these are all the positive control values, and these are the negative control values here. You see there's variability, in the signals. Each one of these little clusters is a different daily run of a batch of plates. But there's still adequate separation between these signals that we can get a good response. And we know if the compound's active, it's up here and not down here. And when we do the Z prime calculation, we can see that these are all above 0.6, which tells us that every plate in the assay runs with sufficient robustness to have confidence in. And let me just say that we run the controls on every plate. We run 24 positive, 24 negative controls on every plate to calculate the Z prime factor. The Z prime factor is when you compare control values, we call it a Z prime. When we compare sample values to a control, we call it just a Z value. Okay. So this tells us that our assay is working robustly in every plate. So then finally, the data that we receive from that has to be analyzed. So the data that's generated from the plate readers is first captured and imported into the biology component of our activity-based software for the calculation of the percent CV, the Z prime values, the signal window, and so forth. Then that data is normalized relative to the on-plate control so that we express everything as a percent of that response, and then that's stored in the Oracle database. Then it's there that the data is associated with the compound ID, and then we can do the statistical analysis to identify where the actives are. So again, going back to this idea of normal data distribution, for selecting hits, we rely on this, again, this distribution of data, which says that compounds that aren't active are going to cluster around this the mean for non-active compounds. Most compounds in the screen are not going to be active. So if we analyze all the data in the screen, then it'll have a distribution with a mean value which is around 0, okay? But the compounds that are active should lie out here. They should be active, and they should be separate from this population. So we can take a statistical cutoff of 3 standard deviations away from this mean of all the data and say we're going to take that as our cutoff for where we define a hit in the screen. Okay, and that's only going to contain, that's going to be 0.15% of the data. Now, the thing is, it's important to confirm those hits in a retest. And the reason is because statistically, when you use large numbers of compounds, you can still find compounds that are outside of 3 standard deviations of the mean that aren't hits. So in this example, we have 13,600 compounds. 800,000 of those would be not active in say, a Luminescence assay. They'd have an effect of 0 to 20%. But if the probability, just from statistics, that we would observe 0.15% of those as being outside of 3 standard deviations of the mean, that's still 1,200 compounds. Okay, so we're going to select out of this set of compounds, and it holds true for all of the levels of activity throughout the screen. So we can initially cherry pick or identify 1,355 compounds as active in that screen. But when we retest them, the same statistical parameters of probability will apply, so that in this retest, these 1,200 compounds won't come up active again. Only 2 of them will come up statistically. Whereas these that are real actives, almost all of them come up. So we can, just in the confirmation retest, we usually end up filtering out about half of them for the initial preliminary active compounds from the screen. So it's very important to do that. So the way we do that is we cherry pick, which is a process of just identifying which wells the active compounds are initially. We recollect those into a new, what we call a new destination plate, and then we array those. We can do 320 of those compounds per plate, and then we can retest those compounds, only this time we test them in 10 concentrations, not just 1 concentration. And we do serial 2-fold dilutions through a stack of plates. Okay, so we'll have a stack of 10 plates. Each plate has 1 concentration of each compound. So we can do concentration response curves for 320 compounds in a stack of 10 plates. So that when we measure them, what we can do is collect in the database, we can collect the data from each plate for each compound and reconstruct a concentration response curve, and then we can calculate our EC50 or IC50 values from that. And that tells us not only if the compound's active, but also how potent it is. So hit validation then. So again, if we do a primary screen, say we do 700,000 samples, that's going to be 2,200 3 to 4 well plates. We test them in single kit. Usually takes 11 to 12 weeks to run that. We rescreen those provisional actives through this cherry pick process, confirm them as being active by calculating the EC50 or IC50 values, and then we validate them by eliminating samples that can interfere with the detection system that have off-target effects. So we'll also test them in dose response in an assay that doesn't have the target there, for instance, to make sure that we're not just interfering with the assay signal. So that's part of the final validation step. We also run usually a counter screen to measure cytotoxicity of those compounds, particularly in cell-based assays. So really, this is pretty much the end of the HTS campaign. The only thing left to do really is to engage in a little bit in initial hit-to-lead chemistry. So the chemist, we will identify the clusters of compounds around the hits. Chemistry will triage those based on these the parameters that we give them, plus their own interrogation of the structures. We will test them in secondary assays to confirm that they have the right biology, and then the chemist will select the most promising scaffolds for further medicinal chemistry efforts. And then that involves developing structure-activity relations so that they can design new structures, and then we synthesize them, then we test them, and then we can determine, this new structure in the test, is it more or less potent, and the chemists can go back and forth in iterative fashion and eventually design compounds that are more potent. So with that, that's kind of the end of the HTS process, and then you'll hear about the rest of the drug discovery process in the rest of this course. But these are the people in the group at Southern Research. I've counted 5 of them in this room. Right now, I guess they came for the lunch. Maybe there's 6 of them here. Anyway, but this is, again, a team of highly specialized, skilled people that function in each of these roles in micro screening. If you have any questions for me, that's my email. And again, as Micah mentioned, we're going to have the tour of the lab in a couple of weeks. I did bring a video just to kind of show you kind of what these robots look like. You can see that this robot here has an arm on it that has a plate, and it just put this plate on this hotel, which is incubating in a reaction. So, just in a minute it'll grab it and take it over and put it on another instrument to which reagents can be added.
It's called a hotel?
Yeah, so we call them a hotel where the plates sit.
Okay.
If they're not on an instrument. A hotel or a carousel if it's in an incubator. So put that plate on this machine, and this machine is then going to add liquid to it. You can't really see it from here. And meanwhile, the robot can go do something else while the plate's working here. So you can program it. It's all programmed by computers, so that the robot arms can schedule how they're going to move the plates around depending on what needs to be done and when. So 3 or 4 plates can be being processed on the instrument simultaneously at the same time. Different things going on.
Great, thanks.
Are there any questions?